Welcome everyone to the ML Summer School. My name is Ovirup. I am a principal scientist in the International Machine Learning team in Amazon. And today we are going to dive deep into one of the most important areas in pre-processing in machine learning, the dimensionality reduction. We'll also learn about the related aspect of feature extraction and also feature selection. This will be a section 1 or part 1 in a 3-part module. And in this first part, we're going to build up the motivation for why we even need to reduce the number of features in the first place. We will start by exploring the curse of dimensionality, which is a fascinating phenomena where high-dimensional spaces behave in deeply counterintuitive ways. Our geometric intuition, developed from living in three spatial dimensions, completely breaks down when we move to 50 or 100 or 1000 dimensions. We will also talk about three main families of feature selection: filter methods, wrapper methods, and embedded methods, and also discuss the strengths and trade-offs that make them suited for different situations. And we will close off the part 1 by a refresher on linear algebra, where we will touch upon principal component analysis. So think of today as building the why or the foundational tools, and in the next two sections, you will learn more about the how to actually execute these ideas or techniques. So let us get started. So here is our roadmap for today. We have 8 major stops, and they build on each other in a logical progression. First, the curse of dimensionality, where we will be seeing that why adding more features is not always better and can, in fact, be catastrophically harmful. Second, why the dimensionality reduction matters in real production system. Third, the fundamental distinction between feature selection and feature extraction, two philosophically different approaches to reducing dimensions. We will also cover three selection families in details: wrappers, filters, and embedded methods. We will discuss trade-offs and computational costs for these. We will also have a linear algebra refresher covering covariance matrices, decomposition, and spectral theory. And at the end, we will have all of this connect to principal component analysis, and that will sort of be a segue to the section 2 of the dimensionality reduction session. So as you listen through this discussion, I would highly encourage all of you to think about your own datasets as you go through each section. So you should ask yourself that how many features do you have for the modeling task at your hand, and could you benefit from reducing them or transforming them perhaps? And also think carefully about what type of relations do your features have with the target. So this will sort of allow you to build like better stable models, reduce your iterations, and will also help anchor the theory to your practical experience while actually building these models. So that being said, let's begin with the first aspect of curse of dimensionality. The curse of dimensionality was a term which was coined by Richard Bellman back in 1961, and it refers to a collection of phenomena that arise when you work with data in high dimensional spaces. Our geometric intuition, which we develop by living in 3 dimensions, completely breaks down when you go to 50, 100, or 1000 dimensions. Things that feel natural in 2 or 3 dimensional simply do not hold anymore. Distances behave strangely, volumes shift to unexpected places, and the amount of data that we need to fill up a space grows exponentially. So over the next few slides, I'm going to show you three specific manifestations of this curse, and we'll also understand that why are we calling this a curse. The first phenomena will be something called a volume concentration. The second will be distance concentration, and the third will be an empty space phenomena. So each of these manifestations will have direct practical implications on all machine learning models that you're going to build. And these are not just theoretical curiosities, but these are, these will actually lead to real failure modes for models that you would train for production. So let us start with the volume concentration and see exactly how the geometry of high dimensional spaces defies our low dimensional intuition. So let's look at the first phenomena of volume concentration. Imagine that you have a unit hypercube. So each side goes from 0 to 1, and you inscribe the largest possible hypersphere inside it. In two dimension, the circle uh, would take up about 79% of the area of the square. In three dimensions, the sphere would fill up about 52% of the volume of the cube, which is the first figure we see on the left. And as we increase the number of dimensions, the volume of the sphere relative to the cube does not only decrease, it collapses to zero exponentially fast. By the time we reach 10 dimensions, the sphere occupies only 1/4 of 1% of the cube's volume, like 0.25%. The formula on the slide, which is visible on the left part of the slide, shows that why this is would happen. The volume of the unit d-dimensional sphere is pi raised to the power of d by 2. So it's roughly around 1.5, 1.6 power d. And so which means that the numerator grows, exponentially with d. However, the denominator, which is gamma function of d by 2 plus 1, that grows super exponentially, and we can show this by using Stirling's approximation. We can show that this expression, like the denominator, dominates any exponential that we would have in the numerator. So the ratio as a whole goes to 0 as d goes to infinity. And as we are seeing in these examples, that even at a dimension of 10, the ratio is already 0.25%, so which is already quite low. So the practical implication of this is that almost all the volume in the hyperdimensional cube is concentrated in the corners, far from the center. And if we were to sample uniformly at random inside the cube, almost none of the points will land near the center where the sphere is. This is deeply problematic for any method that relies on the notion of nearby points, because in high dimensions, the geometry of nearness is completely different from what we were expecting based on our intuition in 2D or 3D. So in the high dimension, most of the data would actually end up isolated in corners rather than, being in the central region. So we'll next go over the distance concentration phenomena, which I think is even more counterintuitive. Distance concentration means that as the number of dimensions grow, the difference between your nearest neighbor and your farthest neighbor becomes negligible relative to the distance themselves. The formula on the slide sort of uh, just presents it in a more compact way, where the ratio of dmax minus dmin divided by dmin goes to 0 as d goes to infinity. So what this means is that the gap between the closest and the farthest shrinks to nothing as compared to the distances involved. So let's think about like what this means for an algorithm like k-means. Uh, the whole idea of k-means is built on the idea that the closest neighbors are meaningfully much closer than the other points. But in high dimension, it can happen, say, an example that the five nearest neighbors are at a distance of 9.97, while the furthest point in the entire data set is at a distance of 10.03, say. So the algorithm like might still be able to pick up the five most closest points by sorting, but the choice is essentially arbitrary and extremely noisy. So the same problem also comes up in kernel methods, which let's say some like in an RBF kernel, which uses Gaussian function as a distance. If all the distances are getting nearly identical, all the kernel values become identical as a result. And the kernel matrix carries no useful discriminative information. K-means cluster assignments become arbitrary as a result. Uh, so, like a practical check that you can do uh, given your data, and actually, it's an interesting exercise also that see this observed ratio distribution. So, in your case, if the ratio sort of drops below zero point 0.1, then the distance-based methods like kernel methods Kanin, they are operating on noise rather than genuine structure because it is not able to discern between what's a very far away point and what's a very nearby point as compared to the distance values. So this is a cheap and fast diagnostic and also a good intuitive check you can do before even sort of trying to understand if these models will work or like what will be the fidelity of these models. And it also gives you a good intuition like why it might not be working. The third manifestation of the dimensionality curse that we will discuss is called the empty space problem, and this is really about data requirements. So if we want to cover a space densely enough to estimate things like histograms or local densities, we would need an amount of data that grows exponentially with the number of dimensions. So um, look at the we can take a look at the um, table in the slide, and if with just 10 bins per axis, to have 1 point on average in each of the small hypercubes that is formed by these grids, we would need like exponentially more points as the dimension increases. So that's the issue, that with let's say we are dividing the bins into, and k is in this case not a very large number, like we're not really asking it to do a very granular partitioning. But even with k being 10 and with a dimension of 20, we see that we need like around 1 billion points to get just 1 point in expectation in one of the small hypercubes in the grid. So this is like another, which means that we need like really large amount of data if we are to, really fill up the space in high dimensions. And the really large amount of data is basically exponential. So this is a fundamental reason we need dimensionality reduction. We need to project our data down to a lower dimensional space where we actually have enough samples to fill it, and where neighborhoods could contain enough points to support stable estimation and inference, and where the geometric structure is meaningful enough for the machine learning models to actually learn them well. So so this curse also then gives us the basic motivation that why dimension reduction is really, really important. So, uh, yeah, so we'll just go over some practical consequences of these things, what we already sort of discussed, that KNNs would fail, all the neighbors would be equidistant, and the predictions become random. And will also, the same problem would also affect the kernel methods. And visualization becomes challenging because, hard to visualize data in high dimension. And obviously, as we saw that, we need like a large number of data points to fill up the high dimensional space, exponentially many data. So even the computational cost of storage, processing, like training the models uh, increases. And overfitting, becomes almost like too much common because the models are not able to sort of understand like what is a noise, and because the geometry is not that well captured if we are dealing really in that high dimension. So which means that the models become more susceptible to overfitting and not being able to actually understand the geometry of the data. So we will do a quick check of how much we are able to understand the concept of curse of dimensionality. So we will go over a short quiz. So the read the question on the slide. You have 1000 samples, 500 features, and you train a k nearest neighbor classifier with k equals 5. So what happens in this case? So let's walk through three possibilities, and the question is to sort of pick up which one would be seems more plausible or reasonable given the background that we just covered on curse of dimensionality. So the option A says that it works well because KNN is non-parametric and flexible. That sounds appealing, but being non-parametric does not save us from the curse of dimensionality as such. Non-parametric just means that we do not assume a particular functional form, and it actually is not a statement about the geometry of the space. Option B says that it fails because distances concentrate and all neighbors are equidistant. And option C says that if we increase k in the KNN classifier to, let's say, to 50, then like the distance or rather the classifier would start performing. So I'll give a pause for 20 seconds, and you can sort of go through the question and the idea here, and then I'll sort of reveal the answer and discuss the options. Okay, so I think like maybe you had a chance to um, sort of think through the options, and like the correct answer is B. And the reasoning is that we have 500 dimensions and only 1000 samples, and the ratio of basically, which means like just two samples per dimension. And as we were seeing that which means that we are like like heavily in the regime of the curse of dimensionality. And the concentration of distance means that the five nearest neighbors are barely closer than the farthest points in the dataset. And the decision boundary that the KNN is creating is essentially random. The fix is to reduce the dimensions first get down to a subspace where the dimensions are meaningful again, and then again apply KNN. And I think that's the crux of the idea that we are going to learn and apply today. So why dimensionality reduction? I think we gave, now you have a solid foundation or understanding of why high dimensions are problematic. And now I think we are in a position to discuss what can we actually do about this. So I'd like to frame this around three distinct goals for dimensionality reduction. Um, and every DR technique, like the dimensionality reduction technique that you will encounter, serves at least one of them. So the three distinct goals are: one is visualization, two is compression, and three is noise reduction. And understanding which goal you're optimizing for, determining which method you choose. So, we will go over the techniques in a little bit in the later slides and in the maybe in the part 2 and part 3. But the question that you should be asking yourself, or the mental model that you can have, is that what is the primary goal here? So are you trying to look at the data to gain insight, or are you trying to reduce storage or speed up training, or are you trying to reduce the noise to improve model performance? And the answer to that question should guide your choice for which type of DR technique would be applicable for your use case. So these are the three goals for DR that I was mentioning. So we have visualization, and we have compression, and we have noise reduction. So in visualization, genomics team might want to plot gene sequences, or in 2D to spot some patient subgroup, or to understand some phenomena about some diseases or anomalies. In compression, let's say a streaming service might store lower dimensional data to be able to process it faster, send it through network faster, and so on. And in noise reduction, an example would be like a quant team might want to reduce, noisy signals or noisy inputs to form a more informative signal or stable covariance estimate to inform their predictive models. So let us now discuss one of the most important hypotheses, the manifold hypothesis, which talks about why dimensionality reduction even works at all. It works because of the manifold hypothesis, which is arguably the single most important assumption underlying all of modern machine learning. The manifold hypothesis says that real-world high-dimensional data does not fill the entire ambient space uniformly. Instead, it lies on or near a low-dimensional manifold embedded within that high-dimensional space. So simply think of manifold as a smooth curved surface, and how we see it on the right hand figures, where we see a three-dimensional um, space, but really a two-dimensional plane is embedded inside it, and the data points are actually lying on that two-dimensional surface and not arbitrarily scattered through the three-dimensional space. So although this two-dimensional surface is present in the 3D space, the dimensionality of the manifold itself is not three-dimensional. So it is effectively like a 2D. So why does this matter to us? because if the manifold hypothesis holds, and it almost always does for naturally occurring data, then dimension reduction can find the low dimensional structure and project the data onto it without meaningfully losing any signal. And what we lose is only the noise in the directions that are orthogonal to the manifold. So this is the theoretical foundation that justifies everything we are studying today in modern machine learning. The curse of dimensionality, sort of tells us that the ambient space is too large, and the manifold hypothesis tells us that the data does not actually need or reside on all those dimensions. Yeah, so I mean, just a recap on why DR matters in the production ML. So one is storage, speed, generalization, interpretability through visualization, and denoising. And so how these two sort of relate is that, I mean, the manifold hypothesis sort of tells us that yes, indeed, if that is true, and it is always true for most naturally occurring data like images, text, or even like other types of naturally collected data, yeah, irrespective of whether it is tabular, graphical, whatever it is. So it would lie in a low dimension, and then we'll which gives us the benefit that we can improve the storage, speed, generalization, interpretability, and noise reduction. So now we arrive at a fundamental fork in the road where we want to reduce the number of features, and we have two philosophically different approaches. And understanding this distinction is crucial for making the right choice in practice. So first, feature selection means that we keep a subset of the original dataset columns that we have. And the big advantage of this is interpretability. And the down the downside is that the search space is combinatorial, that which exact subset of features that we want to keep. The feature extraction takes the opposite approach in the sense that it creates new features that are combinations of the originals. But the because new features are formed by combination of existing features, these are no longer directly interpretable in a real world sense. So like both have their own pros and cons and are ways to reducing dimensionality. And if we need like to give importance to the explainability, like, and if the business stakeholder or to let's say in some cases due to compliance we need to give more interpretations, then obviously we'll have to have give more importance to feature selection methods. And if we are purely interested in performative or prediction performance, then like maybe feature extraction is a superior technique. But I think uh, that's just a very high level rule of thumb. So this sort of taxonomy diagram gives us a full landscape of the dimensionality reduction methods. And I would encourage you to keep this mental map as you go through this session and also the next two sessions, uh, as you will learn a lot about these specific methods in this one and the next few sessions. So on the left, we have a branch, we have the feature selection, which splits into three families. Filter families score each feature independently using metrics like mutual information or variance. Embedded methods perform selection during model training through mechanisms like regularization, like in lasso ridge regression. And wrapper methods use downstream model itself to evaluate the feature subsets iteratively, which is powerful but computationally expensive. On the right branch, we have the feature extraction, which splits into nonlinear and linear methods. Linear methods create new features as a combination of the originals, and nonlinear methods like TSNE or UMAP and autoencoders capture curved manifold structure, and that the linear methods cannot capture. So they have more computational complexity, but they're also are able to capture the geometry for nonlinear spaces better. Uh, at the same time, having less interpretability, as we were discussing. Next, we will go over wrapper methods. Wrapper methods are the most intuitive but most expensive approach. We treat the model as a black box, try different feature subsets, train and evaluate with cross-validation. The strength lies in capturing interactions naturally, since they evaluate subsets as wholes. However, they are costly as each candidate subset requires a full model fit. There are three strategies of doing this called forward selection, backward elimination, and recursive feature elimination. The core idea or the loop in the wrapper methods is that we select a subset, we train model on it, evaluate with cross validation, and then update based on the results of the cross validation. The total costs becomes the subsets that were tried times the modeling, the cost to fit the model, times the cost to perform cross validation. For logistic regression, this is maybe possibly manageable, but for costly models which are costly to train, like neural networks, this is prohibitive. Wrapper methods are mostly practical for fast models and under, when we have less number of features, so the possible number of subsets are low. Beyond that, we should consider what are called embedded methods. Uh, we'll discuss forward selection in this context, where forward selection starts empty and greedily adds one feature at a time, keeping whichever gives the best improvement. And this is much cheaper than an exhaustive search. The limitation is that it is greedy, so it cannot discover interactions where two features are useless alone but powerful together. So, although this is but this using this sort of also requires some amount of appropriate understanding of the informative features in the sense that which ones have more marginal value. So backward elimination starts with all the features and removes the least useful at each step. The advantage is that it captures interactions naturally because since the starting, all the features were included. Um, so if two features are only useful when they are present together, then removing either one hurts. So both ones are kept. So in that way, some of the interactions are naturally preserved. However, for large spaces, the cost becomes quadratic in the number of features and it becomes a bit costly. And finally, we have the recursive feature elimination. So RFE trains a model, ranks feature by internal importance scores like Gini importance, and removes the bottom k and retrains the model. So this is much faster than backward elimination because it is using the model weights to guide for the removal than trying every possible drop. So this is obviously like much more practical and useful than the other two in general. So we will next discuss filter methods. So filter methods take the opposite philosophy, where each feature is scored independently against the target, but no model is trained. This is extremely fast and model agnostic, and sort of can serve as a good first cut to go from 10,000 features to 500 maybe before applying anything more expensive. But the limitation is that this is univariate scoring and cannot capture interactions or redundancy. So the pipeline would go like this, that the features go in, they're scored independently using mutual information or chi-square coefficient or the correlation, and then the threshold is set to keep top k based on this scores. And this is fast because this doesn't require model training, this is model agnostic. However, the limitation remains that this is a univariate evaluation. Variance threshold is an idea where if a feature has near zero variance, it is nearly constant and carries zero information. So this again, which shows that the feature itself doesn't have much information or variation inside it to be really useful for the downstream task. So this can also be like a first layer of uh, filtering that can be done. And similarly, Pearson correlation, the covariance divided by the standard deviation. It takes a value between -1 and 1. And, Pearson correlation cannot obviously detect nonlinear relationships. And, but we can still use it to set some thresholds, but the problem is that it will still univariate, and its ability to capture only linear trends. So a better choice is to perhaps use mutual information, where mutual information captures any statistical dependence, linear, quadratic, periodic, or anything. So the mutual information equals 0 if and only if the variables are truly independent. So the only challenge is that the estimation of this is a bit costly and requires binning or KNN-based estimators, which itself introduces some amount of noise. But if you have like more than a few thousand or tens of thousands of samples, so then mutual information would provide a much more informative information than just looking at a Pearson correlation coefficient. And finally, we can also perform chi-square ANOVA type test. Both are categorical. So if both the target and the feature type is categorical, then we can go for chi-square. If it's a continuous target and a categorical feature, we can go for ANOVA F test. If both are continuous, we can go for a Pearson tau test. And if we do not have any as such information about them, we can always go for the mutual information. However, note that these, if we are using the wrong test on the wrong set of pairs, then the test itself may not be meaningful as such. So it is important to understand that what is the null hypothesis for the tests, and if we are using the tests in the right way. So next we'll come to the embedded methods, where embedded methods perform feature selection inside model training. The objective includes a general regularization penalty that pushes coefficients to 0. So no separate selection step is needed. These are faster than wrappers, more powerful than filters, since they see feature interactions within the model. So we will discuss ridge regression with L2, lasso with L1, elastic net combining both of these, and then tree-based importance under the embedded methods. The key idea here is that we add a regularization term to the loss function. Without it, the model overfits with large coefficient. However, in the presence of that regularization, the model balances fitting data against keeping coefficient small. L2 shrinks, but like if we are using a L2 regularization, then it will shrink. but it will never lead the coefficients go to zero, where L1 drives the coefficients going to zero. And we have a mixture of these two, which is the elastic net. So we train one model, and regularization handles selection during that just that single training run, depending on the type of regularization that is used. So which makes the overall idea very elegant and efficient. So I'll go into slightly more details for the ridge regression. Like ridge regression, we are adding a L2 regularization term in along with the original training loss. And we can think of this as a constraint being it's a smooth circle with no corners on the axis. So the solution almost never has any coefficient that exactly becomes zero. So ridge regression with the L2 penalty always shrinks the coefficient proportionally, but never performs feature selection in the sense that it is not making any of the uh, any of the coordinates go to zero, as we see in this picture. So this is good for getting stable performance, and also good in case we have correlated features. So where we don't need to necessarily have a hard selection, like putting any one of them to be zero, but by like reducing the weights in each one of them, or reducing the learned weights, it is actually reducing the variance, but at a very small cost of bias. However, if you want a more hard selection, then we would want to do a lasso regression or a L1 with a L1 regularization. The constraint here takes the shape of a diamond with sharp corners. And when the contour hits one of the corners, at least one of the coefficients is zero, as we can see in this picture. So, which means that this is actually like creating a sparse weight vector by making some of the coefficients zero. So we get a sparse model, and which implicitly means that we have done a feature selection using this just by having L1 regularization in the training objective. So now obviously the down so that's the good aspect of it, but the downside is that this is performing a hard selection. So which means that if we have just correlated features, then it is selecting one versus the other. So whereas maybe we would want both of them to be present but with different weights, but lasso would select one over the other in some way. So if we have like really large number of correlated features, which are like not perfectly correlated but somewhat correlated due to the how the data generative process is, so we have to be careful with using lasso because it will sort of drop out certain correlated features. So ElasticNet sort of fixes both the issues of these two models as we were discussing. So it combines the L1 and L2 regularizations. The constraint is rounded in the corners, but it still sort of tries to do sparsity. So it's we can set up different so the thresholds we set sorry, the coefficients that we set for these regularization terms would determine like whether we are getting a hard selection or we are like leaning more towards the L2 penalty. So let's have a quick quiz. So let's say you have 50 features, many correlated in groups. So which regularizer, would be appropriate? Uh, so Lasso picks one per group, which is option A. Ridge regression sort of shrinks all of them, but never actually makes any one of them zero. And ElasticNet sort of keeps the groups correlated features together and zeroes out irrelevant groups. So which one would be the most appropriate given this setup? So I'll give you around 15 seconds to think, and then we will sort of discuss the answer. So the answer is C, in the sense that it combines the sparsity with the stability of the ridge regression. So, so I think which also it's in general as a practical advice, it is a good practical choice for most scenarios. So, um, I mean, like obviously we can choose to vary the coefficients and or the weightage and the penalties for L1 and L2 and sort of shift one towards the other, but this is a good choice for most of the problems. So we'll also go take a quick look at the regularization paths performed, how basically as the ratio of the weights that we're using in the if we are using an elastic net, then how does it change? So like we plot each coefficient against lambda. So for lasso, the coefficients drop to zero one by one as lambda grows, right? Because we are giving more weightage to the um, lasso aspect. So there, I mean, which enforces sparsity. And in the ridge path, where um, like the L2 has the more weightage, the coefficients shrink towards zero, but they are never reaching it. And the idea is that we want to perform cross validation to actually see, which ones are giving the optimal decision between the sparsity levels and also the performance that we are looking for. So yeah, so that's the like a mental model that we can have, that we can set up different hyperparameters and like obtain a cross validation score and try to get a Pareto of the performance versus the sparsity that we want to achieve. So next we will discuss the tree-based feature importance. So trees decide which features to split on, like gradient boosting trees. If you have worked with models like XGBoost or LGBM, and like give natural, so these models sort of provide a natural way for feature importance, which is the Gini importance. And Gini importance sums impurity reduction across splits, and it is sort of very easy to and efficient to compute in the case of trees. But it is also like slightly biased towards high cardinality features, because those are susceptible to having more presence in more number of nodes. So they would be split much more times, like unnecessarily inflating their importance. And permutation importance shuffles the features and measures accuracy drop. So it is unbiased, but it is a slower approach than the Gini importance, which we pretty much get free when we already have a trained tree model. So in terms of speed, the obviously the Gini is much more fast and in practical sense free, given the training is already done. So next we'll be shifting gears and sort of having a linear algebra refresher. We will sort of discuss some of the foundational aspects, and that will have a segue for us to discuss principal component analysis and PCA. So we discussed the covariance matrix first. So the idea is that we center the work with the centered data, where we have subtracted the mean from the data set, and we're calculating the covariance, which is the like if our data matrix or the center data matrix is X, then the covariance matrix is x trans 1 by n x transpose X. And the diagonal entries in this give the variance, and the off-diagonal entries are providing us with the covariance, the sample covariance. And this matrix is also symmetric and PSD. And this defines like a data ellipse, like the contours of this. So data ellipse in the sense that or like an ellipsoid in a higher dimension. So like if a data distribution is following a normal distribution with this particular covariance matrix, then the contours of that distribution would look like ellipsoids in the high dimension. So eigenvectors are directions which capture the maximum amount of variance in the data. So the definition for them would be like the direction which captures. So the first eigenvector would be the direction which captures the maximum variance. The second one would be the direction which is orthogonal to the first eigenvector and also captures the maximum variance, and so on. So eigen decomposition gives us like a way to capture the spread in the data. And the relationship with respect to principal component analysis is that principal component analysis keeps the top k eigenvectors and discards the rest. And eigenvalues tells us that exactly how much variance are we preserving and how much we are throwing away. So in this picture, if we see, the first principal component is along the direction where the spread is the most, which is the orange direction. And the second principal component is the one that is orthogonal to it and is capturing whatever is the remained or the variance that is remaining after it has been explained by the first principal component. And the eigenvalues lambda 1 and lambda 2 are capturing the variance in those directions. And then by construction or by how the eigenvectors and eigenvalues are defined, so then the first principal component, the eigenvalue corresponding to it, would be the one that is highest. And because the matrix, the variance covariance matrix is a PSD matrix, we would also have the property that the eigenvalues are will always be positive. So we would have the property that if the lambda i's are the eigenvalues, then the lambda 1, which is the first principal component, will be more than lambda 2, which is the second principal component's eigenvalue, and so on. So this brings us to spectral decomposition, which is a matrix factorization of the covariance matrix. So we decompose it as a function of the orthonormal eigenvectors as the columns, and the diagonal, we get a diagonal matrix, which is the eigenvalues, and then we again have the transpose of the orthonormal eigenvectors. And this the variance covariance matrix sigma equals v lambda v transpose. So PCA can be computed. Like, the importance of this is that once we can do this decomposition, this immediately sort of gives us the principal components, right? We need to sort of we just need to sort the eigenvalues in the descending order, and this decomposition is also permutation invariant in the sense that this decomposition will hold even if we permute the v1 to vd, and also like we are obviously permuting the corresponding diagonal matrix. That is, even if we pre and post multiply or like insert permutation matrices, this decomposition would hold. But to get the PCA, we would want the lambda i's to be sorted, and that's where this connects to PCA. So if we are already have this decomposition, then we readily have PCA in some sense. And the Scree plot is a way to see that how much variance is actually getting captured by, let's say, we choose to keep top k principal components. So the summation of the lambda i's from I equals 1 to k divided by the total variance is gives us a estimate of how much is the variance that is getting captured by the top k eigenvalues, and depending on that we can say we'll keep k dimensions, or we need like more. So for example, we would be able to answer questions such as how many dimensions do we need to, or how many principal components do we need to keep to cover for total 95% of the total variance. So yeah, I mean, we sort of discussed what is the connection to PCA, and we saw its relation that if we have the SVD, then that directly gives us the PCA, but obviously getting the full SVD is more computationally expensive. So we also have like other efficient ways to calculate the PCA. So going forward in section 2 and section 3, you will learn more about PCA and nonlinear methods of doing dimensionality reduction. So like a quick recap of what we covered in the first session. So we covered the curse of dimensionality. We covered its three manifestations, and we said that DR in practice will have three kind of uses: visualization, compression, and noise reduction. Then we went over three families of selections, and then we also had a quick refresher of linear algebra, and we covered just the basics of, or the high level intuition of, principal component analysis and how it relates to SVD. So this concludes the session, the part 1, and in part 2 and part 3 you will be covering more around the nonlinear methods.